So I think we'll do a quiz next class and a test next week for college algebra here. You know, the last place we were looking at, in 4.2, we were looking at composition of functions. Let me show you something here. Here's a function, and here's another function. So this was in 4.2. In 4.2 we said, oh, guess what? You can add functions. Cool. You can multiply functions. You can subtract functions. You can divide functions. I mean, that was all okay. But then at the end of that, what we really did that might have been sort of new was we would compose the functions. And so it was f composed with g. And this little circle means composition. So we could do f composed with g of x. And I told you what it meant, but I'll tell you again what it means. It means this. It means f of g of x. And what does that mean? That means take the g function and stick it into the f function. So you're not adding, you're not multiplying, you're not subtracting, you're plugging one function into the other function. That's what you're doing. It's called composition. And I'm starting with this cool example because this cool example is going to lead me into the next section, 4.3. Watch what happens on this particular example. When you plug g into f, that means you grab the entire g function and you plug it into f right there. You know, you plug it in for the variable x. Here we go. It's going to be 3 times x, which is this, plus 7. That's plugging the g function into the f function. And now watch, like I said, watch what happens. When you clean it up, the 3's cancel here. You're left with x minus 7 plus 7. The 7's cancel here, and you're left with an x. And that's kind of new and weird and interesting. Maybe. See, what was the original input to this? Watch this. What was the original input? The original input was an x. Okay, now check this out. You originally input an x, you g'd it. You g'd it. And whatever g did to it, it did something to it. Then you f'd it, excuse my language, but then you f'd it, and whatever, okay, hang on, Larry. You plugged in an x, you g'd it, that did something to it. Then you f'd it. You know what that did? It undid whatever g did. Anyway, the final answer is back to x. You started with an x, you g'd it, you f'd it, and you end up back with x. Let's try it with a number. Watch what happens. Let's do f circle g of a number like let's do 13. All right, so now what does this say to do? This says f of g of 13. Okay, so what does this say to do? Plug a 13 into g. All right, so this is different. When it's a number, you can plug numbers in. When it was just an x, it was sort of, in general, I was plugging the g into the f. Now I got a specific number, so I'm going to plug a 13 into g. It's going to do something. And then I'm going to take that answer and plug it into f. And it's going to do something. But what I'm predicting is that whatever g does, f undoes it and brings the final answer is 13. What I think is going on here is I think f and g are just canceling each other out. Sort of like I showed you here. Here, let's try it with a 13. Plug a 13 into g. Plug a 13 into g. It's 13 minus 7, which is 6 over 3. So it's a 2. So this answer is a 2. What are you supposed to do with that answer? Plug it into f. Okay, let's plug a 2 into f. If I plug a 2 into f, it's 2 times 3, which is 6, plus 7. It's back to 13. Let me check one more thing. I did f composed with g. Let me do g composed with f. does it also cancel each other out? So I'm saying f and g are sort of canceling each other out. Does it work the other way? When you stick f into g, does it cancel each other out? Let me try this. Let me try g composed with f. That means take the f function and stick it into g. Take the f function, yeah, right here. Take this f function and stick it into g. Stick it in there. So here we go. That's a 3x plus 7, and then it's going to be, oops, minus 7 all over 3. Well, I'll be darned. Look what happens. The 7 cancels with the negative 7. You end up with 3x over 3. The 3's cancel. This is an x. What started was an x plugged into f. Whatever happened to that, you plugged it into g. Whatever happened to that, you ended up back at x. F and g undo each other. Cancel each other out. As a matter of fact, just say this with me. Look at this. Tell me what f does. What does f does? What does f do? Let's see. When you plug a number in, you multiply by 3 and then you add 7. That's what f does. All right, what's g do? G subtracts a 7 and then divides by 3. Oh, that's the opposite of f. Hang on, what does f do? Multiplies by 3, adds 7. G subtracts a 7 and then divides by 3. It's doing the exact opposite thing in the opposite order. When that happens, we're stumbling into 4.3 now. When that happens, f and g are inverses of each other. They're called inverse functions of each other. Inverses of each other. They're called inverse functions of each other. That's what 4.3 is about, inverse functions. So I didn't get to here last week. We did a little composition last week, and I'm just now using this composition to start this conversation about inverse functions. When you compose two functions and they cancel each other out or undo each other, they're called inverses of each other. When they're called inverses of each other, they have this special notation. If I have a function called f, then here's his inverse. By the way, this is, we read this, we call this f of x, when we read this. Here's his inverse. F inverse of x. And this is a different function. I mean, in these examples here, it's g. But once I know it's his inverse, once I know f has an inverse, then maybe I call it f inverse. And I have that little -1, f inverse of x. The function is called f inverse. That little -1 is a notation that means inverse. Listen, it ain't an exponent. It ain't an exponent. I know it's up there in the goddamn, I know. Listen, here's an exponent. Now, I don't want to confuse you shit. Listen, when you have 3 to the -1, that's an exponent. Do you know what you do with that? Do you know how to handle negative exponents? I mean, maybe we barely went over it in one of our toolboxes. It hasn't come up too often, but we should kind of know. Well, a negative exponent means it's not a negative answer. It's a small answer. It means move it to the denominator. So I'm going to move it to the denominator and call it 1 over 3. What if I had a 3 to the -2? Move it to the denominator and it's a 1 over 3 squared, which is a 1/9. And hopefully we know that. That's part of our algebra skills. A lot of students will look at this and they'll say -9. Sorry, that ain't what this is. A negative exponent does not make your answer negative. A negative exponent makes your answer small. It makes it a 1/9. Because you move it into the denominator, change it. But anyway, that's a lecture about negative exponents. And what was I trying to do? I was trying to teach you about inverse functions, which happens to have this notation, which I'm telling you is not an exponent. So I didn't mean to go confuse you and teach you about x. This is not an exponent. This is not about 1 over f. It's the inverse of f. And I feel like this is important. You know, mathematics is a beautiful language. It's very consistent. There's hardly any inconsistencies, like, oh, this symbol means 2 or 3 different things. Good luck figuring it out. I mean, that doesn't happen in mathematics. You know, every symbol, it's a very good language. Everything's well defined. Wait a minute, except for right here. I mean, this is a little confusing place in mathematics. This little -1 is an exponent. This little -1 ain't an exponent. And from the context of the way you write it and the way you study it, you should understand when it's a function with a little -1 on it, it doesn't mean it's not an exponent. It means inverse. So it needs to be clarified, right? The language and the notation of mathematics needs to be clarified sometimes if there's any subtle inconsistencies. See, it's an inverse function. It's kind of like his cousin. Remember, I said the word cousin last time I was looking at some functions. You know, what did I say cousin for? I had a function that squared things. And then his cousin was a function that square rooted things. Well, guess what? Those are inverses. I don't think I said it at the time. But they undo each other. One of them squares things, the other one square roots. They undo each other. They're inverses of each other. I also said that when I had the next two. What were the next two? Cubing. I had one function that cubed things, and then I had the other function that cube rooted things. And those are inverses of each other. I jokingly call them cousins. They're inverses of each other. It turns out these two dudes are inverses of each other. So, now I want to teach you how to find an inverse. I guess what I just taught you was if you see two functions, how do you know if they're inverses? If you compose them and they cancel each other out and you get an x. If you compose them and they cancel each other out, then you can test to see whether they're inverses. Then yes, they're inverses. If you're given two functions, you can do this to see if they're inverses. But what if I just gave you a function and said find his inverse? Find the inverse of this function. Here it is. 5x minus 6. Well, I'm going to teach you how to find an inverse. I'm going to teach you my method. I had this one method. I got this method. I'm going to call it the Smith method because I don't think I ever saw this anywhere else. The Smith method says to do this. Write down what f does. What does f does? If you if you plug in a number for x, what do you do to f? I mean, what does f do to this number x? If I plugged in a number x, what would you do to it? You'd multiply by 5, is that true? You'd multiply by 5. I'm going to write that down. You'd multiply by 5. After you multiply by 5, what would you do? Subtract 6. Okay, I'm writing that down. That's what f does. Now, to figure out what f inverse does, I'm going to undo this in reverse order. I'm going to undo f in reverse order. All right, watch this. Here we go. Here we go. Look, I'm going to do this. But I'm just going to start by putting an x out here. Okay, now what am I going to do to that x? What am I going to do to that x? Well, I'm going to do it in reverse order. So I'm going to add a 6. After I add a 6, then I'm going to divide by 5. 2, you got it. That's the Smith method. What do? Write down what f does, and then try to reverse that in reverse order. Do the opposite of that in reverse order. Listen, you kind of need a method. When functions are really simple, you don't need a method. Watch this. Watch this. Here's a function called g. It's 7 times x. What do you think g inverse would do? I mean, I'm suggesting you don't need much of a method. You need this concept, though, of undoing, okay? Kind of, or doing the opposite, or undoing. So if this function multiplies by 7, The inverse function probably divides by 7. Watch this. Here's another function called h. This function takes an x and adds a 3. What do you think h inverse probably does? Subtracts a 3. I mean, these are real super basic ones. This one had a little couple steps, so I came up with a method for you. These are all kind of one-step ones. Watch this one. F of x is the cube root of x. So this function is cube rooting. His inverse would cube it. His inverse would cube it. The opposite of cube rooting would be to cube it. By the way, they're inverses of each other. I labeled him F and him F inverse. I could label him F and him F inverse. They're inverses of each other. Let's do a tougher one. Let's do a tough one. Check this out. This is so much fun. You ready? These long, tough ones are cool. You ready? Here's one. Here's a function, and I want to find his inverse. You ready? This is 2 times parentheses x plus 3. Oh my God. Hang on. Wait a minute. 2 times. Hang on. I'm sorry. 2x plus 3 cubed all over 4 plus an 8. Yeah, this is good. So I want his inverse. This is going to take several steps. The Smith method works pretty good. Let's try the Smith method. The Smith method says, write down what f does. F does. Okay, let's write down what f does. This is really kind of about order of operations. You got to get the order correct here. So if you got to imagine plugging in a little x, and what would you do to it? So if you plugged in a little x, what would you do to it? I think the first thing you would do is multiply by 2. So I'm writing that down. Then what would you do? Add 3. So then you add 3. So then what would you do? Then you'd cube it. I think I'll just write down cube it. After you cube it, you would, well, I think you would divide by 4 because of the way the parentheses are. I mean, the division is just him divided by 4. And then really this plus 8 is out on the end. I think that's last. I would add an 8. You guys with me? I wrote down what f does. And now to come up with f inverse, it isn't that hard really. All I got to do is, I'm going to look at me. I'm going to put an x out here. And then I'm going to start undoing this stuff. Undoing this stuff in reverse order. Here we go. Here we go. What should I do first then? Subtract an 8. Okay, subtract an 8. By the way, whenever you do the next step of this, you do it to the whole thing. So the next step would be multiply by 4. Okay, well, you multiply the whole thing by 4. Put parent, you multiply the whole thing by 4. All right, what's the next step? Cube root, cube root. So I should cube root the whole damn thing. Cube root the whole thing. All right, now what? After I cube root it, I should subtract a 3. That'll just be out on the end. Subtract a 3 there on the end of the cube root. And then divide the whole thing by 2. The whole thing. Yeah. Dude, we did it. This is the inverse function of this. It's hard to tell, but it is. I mean, in one kind of big sense or broad sense, this function, had a lot of crap going on. But this function was cubing. So the inverse function has a lot of crap going on, but it has a big cube root. I mean, in the big thing I see is a cube and a cube root. But there's a lot of other little details going on. There's a plus 8, there's a minus 8, there's a lot of other details, but that's one big idea. That if that function cubes, this function has a cube root somehow, some way. That's pretty awesome, man. That's the Smith method. Let me show you another method, because even though I love the Smith method, I'd like it to go viral or whatever. I don't think it will. It doesn't always work. It fails a couple places. It works pretty good. But here's another method. You ready? Maybe you've heard this one before. Maybe you've never heard this stuff before. I'll call it the book method. It's just kind of the standard method. Let's see. For finding an inverse. Let's go back to this problem. For finding an inverse. Oh yeah, the book method is this. Step 1. Switch x and y. Switch x and y. Step 2. Solve for y. All right. This works too, I guess. Let's try it. So I'm trying to find his inverse. I sort of already know the answer, but anyway, I'm going to do the book method here. The book method says switch x and y. Hold on. Switch x and y. Wait a minute. Oh, this is y, right? This is y. So this is y, so I'm going to call it x. And that's x, so I'm going to call it y. Okay, right. I switched x and y. That's it. That's easy. And now, solve for this y. And solving for this y is going to make you add a 6 and divide by 5, which is exactly what we did before, I think. I'm going to add a 6. I'm going to divide by 5. And that's y. But this y ain't the old y. This y was the switched y. This y is f inverse. I mean, the original y was f. When you switched them, this new y is not f. This new y is the cousin, f inverse. And that's it. And we got that a few minutes ago using the Smith method. But this book method works pretty good. Switch x and y, solve for y. I mean, the truth is, it's the same thing, just sort of set up structurally a little different. But in the end, don't I end up adding a 6 and dividing by 5? I mean, I add a 6 and I divide by 5. It's just more algebraic. Maybe the Smith method is more intuitive. I mean, it's more algebraic. This method is a little more algebraic, but it works. You can do it on this one, but I don't know if I want to. Huh? You're like, yeah, it's kind of more, you get a feel for what's going on. I mean, again, it is the same thing. Watch, if I make that an x and make this make this a y, is that what I'm supposed to do? But see, now I'm supposed to do the algebra to solve for y. So what's the algebra necessary to solve for y? Well, triple 4. Well, no, actually, please don't. Subtract the 8. Which, if you remember, that's what we did before. But subtract the 8, probably multiply by 4, then cube root. To get rid of the cube, you would cube root. And then, anyway, you would do the algebraic steps to get y by itself. But when you do it the Smith method, you wrote down those steps in a way here. So it's whatever. It's the same thing. I mean, it ends up the same, and in a way it's the same thing. It's just a different way of thinking a little bit. All right, so I'm not going to do that. But I do like these more complicated ones. They're like, seem like they're challenging, but in a way they're not that hard. You can do them. All right, so I got some more concepts to teach you about inverse functions. There's some interesting ideas. So I think I just taught you how to find one. Book method or Smith method. Given a function, how do you find its inverse? You got the book method or the Smith method. But watch this. This is a true fact. I'm going to make a little chart for this function f right here. This function f. I'm going to make a little chart. Look, plug in a -2 for x. What do you get if you plug in a -2? Can you help me? The original function f there.
-16.
Thank you, -16. All right, I'm going to plug in a 0. What do you get when you plug in a 0?
-6.
All right, thank you. I'll plug in a 1 and you get -1. Good. I'll plug in a 3 and you get 15 minus 6. You get a 9, I guess. All right, so anyway, he's a function. He's got a thing. He's got values, inputs, outputs, All right, watch this. Okay, this is a different function. It's his inverse. It's his cousin. He's related. You know, let's make a chart for him. Watch this. I'm making a chart for F inverse here. You know, I don't know. Let me just try something. Look, I'm going to plug in a negative 16. I don't know. I'm plugging in a negative 16. You with me? Watch this. Negative 16 plus 6 is negative 10 divided by 5. Negative 2. All right. I don't know. Let me just plug in a negative 6. See what happens. Oh, that's a 0 over 5, so that's a 0. All right. I don't know. Let me try a negative 1. If I plug in a negative 1, what happens here? Let's see. If I plug in a negative 1, I get 5 over 5. I get a 1. You guys notice anything? I don't know. Let me just try a 9. Let me just plug in a 9. I don't really know what I'm doing. I'm just going to plug in a 9. 9 plus 6 is 15 over 5, which is 3. Notice anything? The ordered pairs for the function are x and y. When you look at the ordered pairs for the inverse function, they're all switched. All the x's are now the y's, all the y's are now the x's. You know, in that phrase of in the book's method where they said switch x and y, well, that's actually true. This is true about all inverse functions. The x's and y's are all switched. If you looked at a whole stack of ordered pairs in the function like we are, there's the x's and the y's. When you look at the ordered pairs of his inverse, they're all switched. It isn't just this function, it isn't just these numbers, it's true for all functions, all inverse functions, all functions and their inverses. True concept. The x's and y's are all switched. It's kind of a cool concept. When you go to graph it, watch how that plays out in a graph. Watch. And when that plays out in a graph, I'm going to try this with this x. I'm going to try it with this guy here. I plotted a million points here. The original function is here. Negative 2, negative 16. That's way down here somewhere. 0, negative 6. I'll call that right there. 0, negative 6. 1, negative 1, 1, negative 1. 3, 9. 1, 2, 3, 9. You guys okay? If I connect those dots, this is not the best job in the world, but it ain't too bad. Oops. Oops. It's a line. It's just a line. There it is. It's f of x. You know, we knew what it was. It's a line with a y-intercept of negative 6, slope of 5, actually. That's what he is. All right, check out the other guy. If I plot all these points, watch this. Negative 16, negative 2. He's going to be red. Negative 16, negative 2. Negative 6, 0. Negative 6, 0. Negative 1, 1. Negative 1, 1. 9, 3. 9, 3. All right. If I connect these dots, there's that guy. That's F inverse. That ain't too bad. See what happens when you take all the x's and y's and switch them and then plot them? What always happens is these guys are mirror images of each other. There's some symmetry here. But the symmetry is a little strange, a little hard to see. The symmetry is around this line, this imaginary line right here, or it's a line that I'm going to draw a dashed line right here. This line is a perfect 45-degree angle, right there, perfect diagonal line right through the middle of that. A perfect diagonal line that goes through the origin has a slope of up 1 over 1, up 1 over 1. The name of this perfect diagonal line is called y equals x. This y equals x acts like the mirror for a function and his inverse. This is always true. A function and his inverse are going to be mirror images of each other around this mirror. And you can see it now, especially now that I drew the mirror, right? You can see it. I mean, they're reflections of each other. And when this one comes in and hits the mirror, the other one comes in and hits the mirror. In fact, this one goes into the mirror and through to the other side. The other one goes into the mirror and through to the other side. And they're mirror image reflections. And it's really about these damn ordered pairs all getting switched that makes that happen. Cool, check this out. So now that you've got that concept, I mean, there's two concepts here that are very cool, that are very related. A function and his inverse have ordered pairs that are switched. When you display that on a graph, a function and his inverse are mirror images of each other around this mirror. And this is just always true about inverse functions. So, check this out. Think you could find his inverse function? You didn't know? Did you guys have a you're supposed to have a prerequisite of art? Did you know you're supposed to have art before you came to this class? I'm kidding, I'm just kidding. But somehow you need some, geez, this is kind of hard. I mean, some art does help. Where's the damn mirror? I'm drawing the mirror. This is the mirror. This perfect diagonal mirror is the mirror. And now what I want to try to draw is his reflection. I want to try to draw his inverse. That was the question. Here's a function. Can you draw his inverse? Well, I'm going to try this then. He's coming here. Hey, you know, when this one hits the x-axis, this one's going to hit the y-axis because the x's and y's are switched. This one makes a little bump and then it hits the x-axis again. That's what this one's got to do then. Then it has to go through there. Then he has to hit the what? Oh my God. Then he hits the x-axis again, which means mine's going to hit the y-axis. Then he comes in here kind of close to the mirror, but then he bows out. Dude, I think I did it. It isn't perfect, but it's not bad. That's a little fat right there. But that's the mirror image. That's kind of complicated. I mean, I could have been nicer to you like this. Draw the mirror image. That I went a little crazy. It's just always true about all inverse functions. This is what I'm trying to teach you concepts about these inverse functions. All right, now listen, these concepts start to get a little tougher all of a sudden. See, this gets a little tougher all of a sudden. Listen to, see, there's some theory here. See, here's the problem. Look at this. Look at this black function. See this function that I drew in black. See them? It's a black function. Now let me ask you something. Is it a function? This is getting kind of confusing up here. But is it a function? Does it pass the vertical line test, right? That's what I'm saying. Does that black function pass the vertical line test? I think so. I think it's a function. Okay. What about his inverse, which is the red guy? Is the inverse a function? No, big time, fails the vertical line test. So his inverse is not a function. The original function was a function, but his inverse fails the vertical line test, so his inverse is not a function. All right, so we worry about that. I prefer not to worry about it, but if we're studying math, we worry about that. We want the function to have an inverse that ends up being a function. Listen, I'm not sure how much we're going to worry about it in this class, but I'm going to teach you about it a little bit. Listen, Now listen, so why did this guy fail the vertical line test? I'll tell you why. This red one, this inverse thing, failed the vertical line test, and the reason is by the time we did his beautiful little mirror image, the problem was the original function failed the horizontal line test, which is something I never told you about before, but now it's time to tell you. If your function fails the horizontal line test, by the time you flip him over and look at his mirror image, it's going to fail the vertical line test. And so that's a problem. So let me write down something. A function is called one-to-one. And that is true if the function passes the horizontal line test. What was the original definition of a function? Every x had to have one y. Is that what it was? Every input had to have one output. Every x had to have one y. But if one y had a couple of x's, that was okay. That was the definition of a function. Okay, well, and that meant you had to pass the vertical line test. Nobody ever said shit about the horizontal line test. Okay, but now we are. Now, this is new. What's one-to-one? Well, one-to-one means you pass the horizontal line test. And here's what that means. That means every y better have one x. So also, now wait a minute, it's got to be a function. So that means every x has to have one y, so it's a function. But to be a one-to-one function, now every y has to only have one x. Then it's a special one-to-one function. So what's so great about that? If it's a one-to-one function, it passes the horizontal line test. Therefore, his inverse will pass the vertical line test. If that happens, then that means his inverse is a function. Are you with me? You following my logic? I mean, this leads to this, leads to this, leads to this. So the concept is, if a function is one-to-one, his inverse will be a function. And what does one-to-one mean? It means passing the horizontal line test. But what does that mean? It means for every y, there's only one x. Maybe I should say that. For every y, there is only one x. Only one x. See, it starts to get a little complicated, and maybe we'll get to a point here. Listen, this is college algebra. We do a lot of good algebra in this class. But after this class is called pre-calculus algebra. There's more algebra to come. Anyway, maybe we're getting toward the end, and maybe I want to, anyway. When you go to pre-calculus, you can discuss inverse functions a little more, perhaps, and get into a little more detail, perhaps. But we're there. We're doing good. I mean, there isn't much more to them than what we've discussed. But I'm not a big fan of getting all picky here about this. I mean, but I do have some homeworks that asks you, is the function one-to-one? And you should think about this. Does it pass the horizontal line test? That means it's one-to-one. Or you should think about this. Does every y only have one x? And what the hell's the point? The point is, his inverse will be a function. His inverse will pass the vertical line test. See, like this guy. Look. Here's a function. Now, this function squares things, right? So what's his inverse? What do you think his inverse is?
X, the square root of x.
The square root, right. I mean, that's kind of logical. But if you think about the does and undoes, what this function does is square things. So what this function has to do is undo that. This function square roots things. They're cousins, they're inverses, that's cool. Everything's cool except there's a little problem. This function looks like this, and it fails the horizontal line test. It's not one-to-one. It's a beautiful function, but it fails the horizontal line test. It's not one-to-one. So technically, he doesn't really have an inverse that's a function. I mean, the truth is, his inverse is this. His inverse is this, which is not a function. I mean, when you just switch the x's and y's, this is what it is. And it's not a function. So how do I get around calling that the inverse? I mean, that's a lie, because, by the way, you know what that is, right? What is that? He is a function. What is it? You know what he is. He's the top half. Actually, he's just the top half of this parabola. See, his inverse is this, and it ain't a function. But we want this to be the inverse, which is a function. So that means we go back to this one and we restrict his domain. If we did this, watch this. If you go back to this original function and we try to make him one-to-one, we can make him one-to-one if we say this. X has got to be greater than or equal to 0. If we'd say x is greater than or equal to 0, we've just erased this half of the parabola. Hey, now is it one-to-one? Now does he have an inverse? He does. Now that's on the edge of where I don't want to get all too, restricting his domain ends up restricting his range, but that's what you do to make him be an inverse. Or to make his inverse be a function, you have to do that. I think that's enough of that. Let's not go any deeper into that. I keep looking at that clock. It says it's 10 to 5. What time is it really?
10 to 9.
Oh, it is 10 to 9? Okay, well then it's sort of okay. Sort of, something's accurate about it. All right, you guys. Hey, I just gave you a good explanation about inverse functions. You should try some homework, I suppose. Yeah, let's see what happens. Let's do something else. If I move into 4.4, well, let me say this about inverse functions. Let me just say this. So there's all these little cool details, but on a real basic level, if one function is multiplying by 7, the inverse divides by 7. If one function adds 14, the inverse function subtracts 14. If one function squares things, the other one square roots things, sort of. If one function cubes things, the inverse cube roots things. I mean, that's on a real basic level. You understand inverses. But when there's 3 or 4 or 5 steps involved, then we need some methods and we need some discussions about these functions. But okay, all right, we're moving on. In 4.4, this gets very algebraic here. All of a sudden, we're solving some equations. There's also some inequalities up here. But we're solving some equations, and they can get kind of nasty. This is some good algebra sometimes. This first one's not. Look at this. I want to solve this equation. It's an equation I want to solve for x. Well, this is algebra, you guys, and maybe you know, in order to solve for x, you got to kind of get him by himself, and he's buried up inside this square root. So I think you'd like to get rid of the square root. Any algebraic moves that would help you get rid of a square root?
Square both sides.
Square both sides. Maybe we've stumbled into this already, maybe not, but here it is officially. We square both sides, right? And it's algebra. The step is square both sides. Square both sides of the equation. Square both sides. It's important to understand it. We'll do some more examples where it gets a little more sophisticated. But it's important to understand you're squaring both sides. You're not really squaring each term, although in this example, Squaring this side does mean square that term. What happens when you square a square root?
Nothing. You just take the.
They kind of cancel each other out because squaring and square rooting are sort of inverses. They cancel each other out, and you get 2x minus 3. On the other side, you square 7, and of course you get 49. Now, do you think you can do the rest without me? I do. Right. But I'll help you anyway. Add 3. Divide by 2. And there's the answer. It can get worse than that, and the other funny thing is, when you square both sides, that algebraic step, square both sides, can actually cause you to get to have what's called extraneous or wrong answers. So when you're solving, you should always check your answer. Now, you never hardly see me check my answer. When I do math, I usually do it correct, and I don't have to check my answer. And I don't even really want to check this one. But the truth is, when you do a step called square both sides, it's possible to create wrong answers. And so you should check your answer. What does that mean? Go back to the original problem. The original problem was 2. Plug this x in here. 26 minus 3. Does that really equal 7? That's 52 minus 3. It's the square root of 49. The square root of 49 is, yeah, okay, it checks. I knew this one was going to check. Let's do a better one. Watch this one. The square root of x plus 1 minus x equals. Hang on. Oh, crap. Okay, wait. Don't look. Quit looking up here. Don't look up here. You guys looking up here? Hang on. Don't look up here. Hang on. Hang on. I'm changing that. I'm changing that to a. All right, cool. I think I got this. Look at this little problem. Okay, I think I got a good one. All right, so the question, it's an equation. It's an equation with some variables in it, and the question is solve for the variable, solve for x. Okay, it's also got square roots in it. So we know in order to get rid of these square roots, I'm probably going to square both sides. Listen, I wouldn't square both sides right now, though. What I would do is, when you square both sides, your idea is to get rid of that square root. And so what I would do is get the square root all by itself. So when you square it, when it's all by itself and you square it, it just pops out. So I think I should move the x over. Do you agree? Move the x over first. That gets you this square root all by itself. This is x plus 3 over here. And now you square both sides. Now, square both sides. So that means you grab this and square it, which is x plus 5. And you square this other side. Now, a mistaken algebra student would square this wrong. What would they do wrong?
Square each one individually.
Oh yeah, just square each term. That's why it's the phrase square both sides is so important. You don't square each term. You square the whole side, which means FOIL this out. FOIL it out, which is x squared plus 6x plus 9. Did you know? Is that okay with you? X plus 3 times x plus 3 FOILed out is this. Right. Okay, cool. Now what? Well, we got rid of the square root. Shit, now we got a quadratic equation. Oh my God, how do we solve quadratic equations? Move everybody over, get it equal to 0. Okay, all right. So now I'm subtracting an x. If I subtract an x, that's a 5x. You guys with me? I'm subtracting an x. I'm subtracting a 5 from the 9, so that would be a 4. You guys okay?
Yep.
And now it's a quadratic equation. It's equal to 0. I think it can factor. I think it's x and x. I think it's a +4 and a +1. What a beautiful problem. Look at that. I set each factor equal to 0. You know how to set each factor equal to 0. When you set this equal to 0, you get the answer, x equals -1, and you get the other answer, x equals -4. You guys are with me, right?
Yep.
All right. Woohoo! I got my answers. See you later. I'm done. Oh, wait. What did I say? What did I say before?
It's possible to get it wrong.
Yeah. We better check these damn answers. Right. I mean, I didn't do anything wrong. I didn't do any moves that were wrong, but the squaring of both sides can possibly yield extraneous solutions, wrong answers. We better check them. Okay, I'm going to check them. That means I go back to the original problem and I'm checking x equals -1. Here we go. If I plug in a -1, it's -1 plus 5 minus a -1 equals 3. Yeah, I'm plugging in a -1 for x in the original problem. You guys okay? All right, here we go. That's 4. The square root of 4 is 2. That's plus a 1, and that's 3, so cool. 3 does equal 3. That checked, actually. He checked. All right, I'm going to check the -4. I'm checking the -4. Let's see what happens. The -4. I'm plugging it in. That's the square. That's a -4 plus 5. And then it's minus a -4. And does that equal 3? Let me see here. That's -4. So that's a 1. The square root of 1 is a 1. But this is minus a -4, so that's plus 4. And that's a 5. And a 5 does not equal 3. This didn't check. Please throw this answer away. There's only one answer. And again, it wasn't anything we did wrong. It's just the nature of these problems. Squaring both sides can yield wrong answers. On one like this, when it's quadratic like this, we get 2 answers. So what's the possibilities are, maybe you check them and maybe both answers work. And you got 2 answers. Maybe, like ours, one answer works and one doesn't work. So there's one answer. You know, it's possible when you check both of them, they don't work. If both of them don't work, the answer is? No solution. Right. The only 2 solutions I got didn't check, maybe. Don't screw up your check, though, right? Don't make, I mean, double check your check. Make sure you check your check well. One of them worked, one of them didn't on this one. You know, what if you saw a cube root of 3x plus 1 equals 4? How would you solve one with a cube root? Now you got to solve for x. It's pretty easy, right? I mean, it's very natural to say, well, when it's a square root, you square both sides. When it's a cube root, you should cube both sides. So, no big deal. You grab this and you cube it. And you don't really cube it because, well, you do cube it, but cubing a cube root cancels each other out, and it's real easy. You get 3x plus 1. On the other side, you grab that thing and cube it, and so you cube it. You can pick up a calculator, but it's 4 times 4 times 4. Everybody knows that's 64. And then you proceed to solve. Subtract the 1, divide by 3. That's pretty sweet. That's my answer. Hey, when you cube both sides, you don't really have to check it. It's those damn even roots. It's the square root and maybe the 4th root, and it's the even powers that might produce wrong answers. Anyway, so. Well, So there's a little more in 4-4. But I think I'm going to quit. I think we did enough. So we did good, dude. We're halfway up. We're halfway through 4-4. There's some inequalities in 4-4 that get a little different and weird. So I'll help you with inequalities someday. But I'll see you Thursday, and I think we'll do some kind of quiz.